Okay, we're going to start off talking about how to solve linear systems using primarily Gaussian elimination. And with what we know about Gaussian elimination, then we're going to go on and consider various properties of the solution and show how LU decomposition arises and things of that sort. Okay. The first thing we need to do is we need to get a little bit of notation out of the way. So we're going to first of all talk about what's called the row echelon form of a matrix. And in order to do that, we have to first define what the pivot element of a matrix is. And we're going to say that the pivot element is the first non-zero element in a row of a matrix. That's what we're going to call the pivot element for that row of that matrix. And with that, we can now define what a row echelon form of a matrix is. So we're going to sometimes represent that as REA, just to abbreviate it a little bit. But we're going to say that it's a matrix that satisfies three conditions. First of all the pivot elements are unity. So if we look at this example here, we see that 1 in the first row, 2 in the second, and 1 in the third row are the pivot elements for that matrix, but 2 is not unity, or 1. So that matrix is not in row echelon form. Okay, next we're going to see that the pivot in any row always has to lie to the left of the pivots in all the rows below it. And that's what gives the row echelon form that triangular appearance, right? So if we look at this example, okay, we can see that the pivot in row 2 lies to the right of the pivot in row 3. So that's not in row echelon form. However, we could easily remedy that by simply exchanging the rows, right? And last, we have to satisfy this condition that any row that consists completely of zeros always has to be below any row that has a pivot in it. So if you look at this example, you can see the second row consists entirely of zeros, but it's above rows that have pivots, i.e. rows 3 and 4. Therefore, that is also not in row echelon form. Now, row echelon form is nice, but it's not the optimal way to solve a system of linear equations. We would rather have the matrix in reduced row echelon form. And reduced row echelon form is essentially the same as row echelon form, and we're going to abbreviate it by RRE. It satisfies the first three conditions too. However, it has this fourth condition, which says that if we have a pivot, all of the elements above that pivot in that column also have to be 0. Okay? So this is unlike row echelon form, which if you think about how we define row echelon form, a natural consequence is that for any pivot, the elements in that column below the pivot have to be 0. Well, reduced row echelon also requires us to clean out the elements above that pivot too. So if we look at these three examples, we can see these are all in reduced row echelon form. Okay, they all satisfy these three conditions. Okay? All right. Now, in order to apply reduced row echelon and row echelon form to linear systems, we have to talk about this thing called an augmented matrix. Okay? And an augmented matrix for a given linear system, AX equal to B, is simply a matrix that has m rows and n plus 1 columns, where the last column is the coefficient, or the right-hand vector B. All right? We usually draw it with this bar between the coefficient matrix and B just to make sure that in our mind we understand which is which. And the goal of Gaussian or Gauss-Jordan elimination is to use operations on that augmented matrix that don't change the solution. And these operations have a special name that we're going to talk about in a minute. They're called elementary row operations. And these elementary row operations, they have a special, they're specially designed so that they end up putting the coefficient matrix in either row echelon form, and when we do that, we call that Gaussian elimination, or they go a little bit further, putting it in reduced row echelon form, in which case we call that Gauss-Jordan elimination. And the idea is that if it's in row echelon form, you should be able to convince yourself that you can back solve for the solution vector x. And if it's in reduced row echelon form, it's very easy to see that you can directly obtain the solution. Okay? So what are these operations that we're calling elementary row operations? Well, it turns out that, as we said, these are operations we perform on the augmented matrix to put the coefficient matrix in row echelon or reduced row echelon form. And the key thing you want to know is that there are three such elementary row operations. Okay, first of all, we can interchange any two rows in a matrix. Sometimes people assign the types of elementary row operations with Roman numerals, and I'm going to do that. We call this a type 1 elementary row operation. Or we can multiply any row by a non-zero real number. We're going to call that a type 2 elementary row operation. And the last one that you're probably most familiar with is when you add a multiple of one row to another. And that's a type 3 elementary row operation. Now, there are two things about elementary row operations that you should both know and be able to prove. And the first of these is that every elementary row operation can be represented as a matrix, and the matrix representation for the elementary row operation is invertible. So this says that I can perform an elementary row operation by multiplying the coefficient matrix times a matrix. And we're going to call that matrix the elementary row matrix. It's going to perform the elementary row operation. The next thing that's very important is that elementary row operations, whether we perform them manually or whether we perform them using matrix multiplication, do not affect the solutions of a linear system. So I want to look at these two statements in a little more detail. Now, to understand elementary row operation matrices, let's just look at the matrices corresponding to the three operations. Okay, if I want to switch rows I and j in an m by n matrix, all I do is I take the identity matrix and I simply swap the ith and the jth rows. Okay? And we know computationally how to do this, and it's usually easy in most computational packages. This is the MATLAB command for switching the ith and jth rows of a matrix A. So I claim that multiplication of the coefficient matrix by this matrix will perform the operation of swapping these two rows. And if you're unclear about that, you should actually sit down and kind of work this out. Look at this and convince yourself that this matrix does exactly what we say it does. Now, what is the inverse of this matrix? We made a claim that every elementary row matrix was invertible. Well, it turns out that it's its own matrix. It's its own inverse, sorry. And of course, this makes perfect sense. If we take a matrix and we switch rows I and j, and then we switch them again, we get back to the original matrix. Okay, so it is its own inverse. The next two are pretty easy to also construct. If we want to multiply the row I by a non-zero number k, we simply start with the identity matrix again. This is always how we construct elementary row matrices. We construct them from the identity matrix, and we simply multiply row I by k, or in other words, we make the ith element k. Okay. Its inverse is easy to take. Since k is non-zero, I can simply take the identity matrix and put 1 over k and the ith position, and you can verify that that matrix times this matrix that I claim is the inverse will give me the identity matrix. For type 3 elementary row operation, we want to add a multiple of row I to row j. So we want the final result to be in row j, so it makes sense to take the identity element. I'm going to make the jth ith element k and keep everything else the same. And that's going to perform this operation. How do we undo it? Well, we subtract the same multiple of row I from row j. So now if I take that same identity matrix and simply make the jth element minus k, that's going to be the inverse. And again, I leave it to you as an exercise to show that this is the inverse, in fact. Okay? Now, elementary row operations are kind of good to get some practice with. So here are some practice problems that you can do. You can do these on a computer, you can do them by hand. It's not a bad thing to do it on computer necessarily, just to kind of get used to doing this. So we want to give the elementary row matrix that for a 3 by 4 matrix will exchange rows 1 and 3 and show that this matrix is its own inverse. Okay? For the type 2, go ahead and construct an elementary row matrix that will take a 2-5 matrix and it's going to multiply row 2 by 3. And construct the inverse for this elementary row matrix and then verify that in fact it is the inverse. And last, for the type 3, let's go ahead and construct a matrix for an elementary row operation that will operate on a 3 by 3 matrix and add twice row 1 to row 3. And similarly construct the inverse and verify that in fact it is the inverse. Now we made a statement that the elementary row operations do not affect the solution, and I want to prove that statement. So we want to show that x satisfies the linear equation ax is equal to b if and only if x satisfies the equation a prime x is equal to b prime, where a prime and b prime are the result of the elementary row operations on a and b respectively. So we have to prove it in both directions. If and only if means we have to prove, first of all, that if ax is equal to b, then x is also a solution of a prime x is equal to b. But this is easy because if we suppose that x satisfies our original linear system, we simply multiply it by a sequence of elementary row operations, okay, to put a in the row echelon form, and we're done. So it's just a direct constructive proof. Okay. Next, we want to prove the backwards direction. We want to prove that if we satisfy the reduced row echelon form of a linear system, we satisfy the original linear system. And this comes just from looking at the structure of a prime and b prime. Notice that they're equal to some matrix E times the original matrix or vector, and E is this product of elementary row operations. Suppose we did small p elementary row operations, okay? Now recall that the elementary row matrices are all invertible. So this means if I simply multiply both sides of my original system by the inverses in this order, I'll get back to my original system. Therefore, x satisfies my original linear system too. Okay, that does it for this part. Next, we're going to go into LU decomposition and talk about how that builds off of what we know about solving linear systems using Gaussian elimination.